Motional EMF is a special case of induction, and it arises because when charges move in a magnetic field, they experience a force. If we have a conducting rod and move it through the magnetic field as shown, let's imagine what the force would be on the positive protons in the atoms of the wire. They are moving to the right, and the magnetic field is into the screen. So the force, by the right-hand rule, is upwards. Now we know that the protons aren't free to move in a solid, but the negative electrons are, and they will feel a force in the opposite direction, which is downwards. That means that the electrons will congregate at the bottom of the bar, leaving a net positive charge at the top of the bar, and so an EMF is created between the ends of the bar for as long as we keep the bar moving through the field. Let's now think about the conducting bar connected to a resistor like a light globe. The EMF is now making a current flow in the globe. Because current is now flowing upwards through the bar that is moving to the right, the bar experiences a force in the direction opposing its motion. That means you need to keep applying a force to the bar to keep it moving, and that force is doing work. Let's now think about the conducting bar connected to a resistor like a light globe. The EMF is now making a current flow in the globe. But the current is now flowing upwards through the bar that is moving to the right. And so the bar will experience a force in the direction opposing its motion. We know that it must oppose the motion because that is Lenz's law. So that means you need to keep applying a force to the bar to keep it moving, and that force is doing work. I'm now going to show that the work done by the applied force is equal to the energy delivered to the globe. Now we have two parallel rails here that are metal, and we have a metal bar of length L that can slide along them. And that makes a circuit that can power a light globe that has resistance R. And so in here we've got magnetic field, and we will say that the bar is the distance x away from the end of it. Now there's going to be a force applied. So F-app is the force pushing the bar along, because there'll be an induced current flowing in that whole circuit that will power the globe. And so we're going to push it at a constant speed V. Now we'll say that R is the only resistance in the loop. We know that the magnetic field is at right angles to the area of that rectangular loop. So we can say that the flux equals B times A equals B times L times X. So then the EMF, which is the rate of change of flux, is going to be minus d dt of BLX. And B is a constant, L's a constant, and dx dt, which is the rate of change of the distance, is just the velocity v. So the current then is E over R, which is BLV over R. Now, this applied force is doing work because it's moving through a distance. And that will be the applied force times x. So the input power, which is the rate of doing work, is going to be just the force applied times x over t, so that is just applied force times v. Now the power to run the lamp is going to be, well, in the globe, P is VI, so we'll call that P out, that can be P in, and that is VI. Now we know, in fact, For this case, it's the induced EMF times I. Now the induced EMF is BLV times BLV over R. So we have B squared L squared V squared over R. But our input, remember the P input, which is the applied force, times V, we can say that the applied force is equal to the magnetic force, because that force is opposing. That is why we must be doing work to push the bar, and that applied force is B times I times L. So that then we can say that our input power is going to be B I L times V, and we know that I, so that is B times BLV over R times L times V, and that ends up with B squared L squared V squared over R. So the power, which is the rate of adding energy to the system by moving the bar, is equal to the power that is being dissipated by the globe.